Hello and welcome. This is Cambridge O-Level Chemistry Paper 4 Alternate to Practical. The subject code is 5070. This is May-June 2024 exam. This is version 2 of this paper. The hour given to us is 1 hour. So before we start this exam, I would request you to kindly subscribe the channel and pass it on to the friends and family who are going to give the O-Level exams this time. Thank you. Let's start. First question. It says, a student finds the amount of iron 2 ions in a solution by titration. The student uses a volumetric pipette to add 20 centimeter cube of iron 2 sulfate to a conical flask, then adds approximately 20 centimeter cube of dilute sulfuric acid, but then slowly adds aqueous potassium manganate to the conical flask until the solution turns pink. Then repeat the titration several times. So part 1, figure 1.1 shows the apparatus the student uses to measure the volume of the dilute sulfuric acid. Name the apparatus shown in figure 1.1. So this apparatus is a measuring cylinder. Measuring cylinder. Okay. So next part 2, it says why. Explain why the student does not need a volumetric pipette to measure the volume of the dilute sulfuric acid. Okay, so let's see. Here it says add approximately 20 centimeter cube of dilute sulfuric acid. So we do not need a very precise volume of sulfuric acid. So a burette would be perfectly fine. So it says precision is not needed as the student requires approximately 20 centimeter cube of sulfuric acid, H2SO4. Okay, so that is how. Then part 3, it says describe how the student uses the volumetric pipette to measure 25 centimeter cube of aqueous iron 2 sulfate safely. So remember, with a pipette, you always either you have to suck it with your mouth, or you have to use the pipette sucker. That is a you can say a rubber material made up. Also, that is a rubber shape blob made up of rubber. You can squeeze it by fixing it over the pipette, and that basically sucks the fluid from any beaker or volumetric flask for you. So we just simply say the student can use a pipette sucker to safely fill up the pipette. Okay. Then it says part B, name the apparatus the student uses to add aqueous potassium manganate to the flask. You can just simply say burette. Burette. So remember, the burette is a long conical shaped thing that comes up with this knob, and this burette can something like this. So this is a burette, and that burette can be used to add potassium manganate to the flask. So let me draw the flask for you. So this is, for example, the conical flask for you, which contains other liquid. Again, moving ahead, part C, it says, state why the student does not need to add an indicator for this titration. So remember, we are already adding potassium permanganate, so that the color of the solution is initially purple, and that will turn to colorless as soon as the titration proceeds. So we do not need an indicator. So the answer will be the color of the solution changes at the completion of the reaction. That is purple to colorless. Okay, so therefore no indicator is needed for this reaction. Then part D, it says explain how the student knows when they have done enough titrations. Oh, so a good answer would be, or if you are doing the titrations, the error in the volume should be approximate, or should be, or you can say error. Let me write it below so that it will be easier. So error in readings should be less than equal 10% of the values. So whatever the value, whatever the volume you are calculating, your error must be less than or equal to 10% of the value. So here you are approximately getting 20 centimeter cube. So 10% of it will be approximately 0.2 centimeter cube. So just you can write, so if the results are less than 10%, you can say are less than 10% of each other, are less than 10% of each other. You can say it of if the results are less than 10% of each other, that is one answer. Or the other way to write it as if the results are 0.2 centimeter cube of each other. So if you are getting these results, then the student will know that they have done enough titrations and their results are within the 10% error or the 10% ballpark of each other. Okay. So moving ahead, question number 2, it says student investigates the temperature change when solid completely dissolves in water. The student, number 1, measures 25 centimeter cube of distilled water and pours it into a beaker. Then uses a thermometer to measure the initial temperature of the water in the beaker. 3, records this temperature in table 2.1 at 0 seconds. Then adds a sample of solid into the beaker and starts the stopwatch. Then stirs the mixture and record the temperature at temperature and time at 60 seconds interval for a total of 300 seconds. Some of the results are shown in table 2.1. Okay, so the table is shown. So 0 to 300, and there are 2 missing parts. So we have to basically see what is the information given to us to fill them. So part A, it says figure 2.1 shows the results of 120 seconds and 300 seconds. So at 120 seconds, we can see the temperature. So the temperature is little above than 11. Oh, sorry. 11, 12, 13. So this is approximately 13.5. And this is completely 15 degrees C, and this is 13.5 degrees C. Okay. Record the values. So the nearest to 0.5. So they are also saying us to 0.5. So it means that it is equal to 0.6. So at 120, we have 13.5. At 300, we have 15.0. So remember, writing it in this format will be good because all the readings are shown in this format. So to 1 decimal place. Okay, then it says part 2, calculate the maximum temperature change in the evaluation. So maximum change, will be maximum value minus minimum value. Okay, so the maximum value we can see in the table is 19.5. So this is our max value, and the minimum value is this. This is our min value. Okay, so the maximum value is 19.5, and the minimum value is 13.0. The answer will be 6.5 degrees C. So it will be 6.5. Okay. Moving ahead, it says part 3, describe the trend shown in the result or results in the table 2.1. So what is the trend? So if we see, if we just say this is our time, this is our temperature. So what is happening? Say this is 20, this is 10, this is 15, for example. This is 1, 2, 3, 4, 5, 6. So this is 60, 120, and so on. This is 300 seconds. So temperature initially falls from somewhere here to a value of, so initially at 0, the temperature is this, it falls to somewhere here at 60, then almost here at this, until it goes, it's like, so it goes something like this and comes like this. Okay, so what we see here is that the temperature rapidly falls initially, then starts to increase at a steady rate. So it rapidly falls, and and the rate of increase from here is 0.5, 0.5, 0.5, 0.5. So this rate of change is 0.5 degrees centigrade per 60 seconds or per minute. You can also write it as like this. Okay, so just simply write here, describe. You have to describe the change. So could be the temperature rapidly decreases in first 60 seconds and then starts to increase uniformly at 0.5 degrees C per minute for next, you can say 4 minutes. Okay, so this is the trend which we see here. Then part 4, it says suggest the temperature of the mixture if it is left for 60 minutes. So it means that for 60 minutes, 1 minute 60, it is approximately 60 into 60, 3,600 seconds, lots of time. So we have only measured till 300 degrees C. So we can easily say that the temperature will reach the room temperature or the initial temperature or the ambient temperature. It will. So initially, before the reaction started, the initial temperature was 19.5. So it will be 19.5 degrees C. So the explanation, the solution will return to the ambient slash room temperature. Okay, so explanation is, and the reason because of transfer of heat from higher medium to low medium till there is no transfer. So this is low temperature region. This is high temperature region. So the heat will flow from higher to low till there is no transfer. Okay. Uh, then part B, it says describe energy change when solid dissolves in water. Explain how the results in table 2.1 supports your answer. So description, the energy change, it's an endothermic reaction. Uh, endothermic reaction takes place, okay, not takes place, not places. Okay. The explanation is the temperature of the solution uh, decreases when the solid is dissolved. Okay. Moving ahead, it says part C, explain why it is important for the student to stir the mixture to have uh, a uniform homogeneous temperature across the whole mixture is the key reason, and to ensure the solid completely dissolves. So let's write down to ensure that the solid is completely dissolved and the solution has achieved homogeneous slash uniform temperature across itself. Okay. Then part D, it says the maximum temperature change calculated is not the true value for the investigation. Okay. This may be because the volume of water and the temperature are not measured precisely. Explain how to obtain more precise measurement of temperature. So remember, we are measuring with the help of a thermometer, that is measuring. The minimum measurement unit is 1 degree C. Okay. So a more precise thermometer or can be used, or a digital thermometer can be used, that can give you values up to 2 decimal places or 1 decimal place. So use a digital thermometer. Oh, 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 oh. Use a digital thermometer with precision of, or proceed with precision up to 1 decimal place, or the second answer can be use a thermometer with better uh, slash more precise graduated scale, or you can bracket, that is less than 1 degree C measurements are possible. Okay, so these are the reasons which you can write. Any one of them would be a good reason for your answer. Then part E, it says the maximum temperature change calculated is less than the true value for this investigation. Suggest a reason for this other than the precision measurements. Describe the improvement to the method which reduces this error. So what has happened? See, this is a beaker you have. This is your stirrer. Uh, this is your liquid. So this is having low temperature. This is more temperature. So heat will flow from here to here. So it has actually gained some energy from the surroundings via temperature gradient or the temperature difference. That is the reason. Improvement, you have to stop this gain of or this movement of heat from a higher gradient to a lower gradient. And that can be done with multiple manners. Use a plastic beaker, or you can insulate the beaker with certain material, or put a lid over the beaker as well. So these are all reason. A good reason can be, or the one I like the most, is to place insulation across the beaker. And the reason is heat gained from surroundings via temperature gradient, or okay, or you can also call it as temperature difference. And the improvement, insulate the beaker to prevent heat flow. Okay, this is the reason. So moving ahead, question number 3, it says a student does a series of experiments to investigate solution R. Part A, section 1, it says student leaves a wooden splint with one end dipped into R for 10 minutes. The student then places a damp end of wooden splint into the flame of a Bunsen burner with air hole open. The student concludes that R contains sodium ion. State the observation which allows students to make this conclusion. So basically, the student is doing a flame test. Okay. And at the table given at the end of your exam, or if this paper, you'll have the complete, information of what a flame test for sodium will look like. So flame color will be yellow. Simply just yellow flame is observed. Yellow flame is observed. Okay. Then part 2, it says explain why air hole on Bunsen burner must be open when doing this flame test. So basically it ensures or to ensure complete combustion of air with a blue flame. Okay, reason, because why we need a blue flame? Because when we are having incomplete combustion, our flame will not be blue. An incomplete combustion flame is yellowish orange, and you will not be able to see the yellowish flame of sodium if your air hole is not completely open, or you're getting incomplete combustion with the Bunsen burner. Okay. Then part B, it says the student adds dilute nitric acid to R. The student observes effervescence of colorless gas, which turns lime water milky. State conclusions for these observation. So the conclusion number one, the gas is carbon dioxide. This is one conclusion. The second conclusion is that the solution contains carbonate ions. So this is again, remember, 2 points. So you have to, it means that the examiner is asking you for two observations. So these are your two observations. The carbon dioxide, or you can say carbon dioxide gas, is carbon dioxide gas is released. Number one. The second is the solution contains carbonate ions. That is CO3 to negative. Okay. So these are your two observations. Then part two, it says the student adds aqueous barium nitrate to some of the mixture in part B1. The student concludes that R contains sulfate ions. State the observation which allows the student make this conclusion. Observation again from the end of the at the end of your exam or exam booklet, there's a test for sulfate ion. It basically says that when you add barium nitrate, a white precipitate is formed. So just simply write white precipitate is observed. Okay, so then part three, it says student adds aqueous silver nitrate to some of the solution. The student observes a colorless solution. State the conclusion for this. So it means that silver nitrate is a test for halides. So it means that the solution does not contain halide ions that are chlorine, iodine, and bromine are not present. Okay. Then moving ahead, part four, the student adds aqueous sodium hydroxide to R and warms the mixture. Describe the test and observation to show R does not contain ammonium ions. So the test for ammonium ions is that when you heat the solution in presence of sodium hydroxide, ammonia and a piece of aluminum, ammonia gas is released. And when ammonia gas, it turns red litmus paper blue. So the test is use a damp red litmus paper to test the gas. Observation, no change in color of the litmus paper. Okay, so the ammonia gas would have turned damp red litmus paper blue. Okay, then part C, solution R is made from a mixture of two ionic compounds. Suggest the names of these two compounds. So one of the compounds, it says sodium, that is Na. Also, there was presence of sulfate ions and there was presence of carbonate ions. So number one can be sodium sulfate. Formula is Na2SO4. Okay. Second one is sodium carbonate, Na2CO3. Okay, so Moving ahead, part D, it says the student tests a different solution P and finds it difficult to decide to whether the solution contains chloride ions or bromide ions. Okay. The student also has aqueous potassium chloride. So remember, potassium chloride is KCl and aqueous potassium bromide KBr. So just how the student could use aqueous potassium chloride and aqueous sodium bromide to make it easier to decide whether P contains chloride ions or bromide ions. Okay. So what the student will be doing? So you have a solution of, say, so this is the solution of P. So the test for chlorine ions and bromine ions is add HNO3 plus silver nitrate. Okay. So if chloride ions are present, a precipitate, or you can say, let me check from the table. So with chloride ions, you will get white precipitate. With bromide ions, you will get a creamish precipitate. So it is very uh, it's a good possibility that uh, the color of the precipitate becomes a little difficult. Okay. So what you can do is that you'll uh, add KCl to the mixture P and do the test, record the or you can just simply add you can say dilute nitric acid and silver nitrate to the solution of KCl, observe the precipitate, then do the same in potassium bromide and observe the precipitate, then repeat the process with B and compare the color of precipitates, and then you will have your answer. So let's write it down. Uh, add dilute HNO3 and AgNO3 to a solution containing KCl, record, or you can say observe, and record the color of precipitate, repeat with KBr solution, okay. Then now add HNO3 and AgNO3 to sample P, observe the precipitate, and compare with the ones observed with KCl and KBr solutions. The identical ones will give you the presence of the ion. The reason for this question is because sometimes it becomes difficult to differentiate between white and creamy precipitates. So this is a good test that in a test tubes, in two separate test tubes, you had a little potassium chloride and potassium bromide. Do the test with them. So you have a complete sample of what white color with chloride looks like and what creamish color with bromine looks like. Or and then just simply do it with this your sample and compare your result with both of the colors that are present with you in the test tubes, and the one that matches the most is your uh, the you can say ion which you are looking for. Okay, then moving ahead, part E, it says the student adds dilute hydrochloric acid to another solution and a gas is produced. The gas is passed through lime water. Describe how the gas can be passed through lime water. You may draw a label diagram to help your answer. Okay, so let's see. We have a conical flask. Oh, can pardon my drawing here. I'm trying my best to draw it. Say, for example, this is your conical flask. This is your solution. This is your rubber cork that is holding it. So you have a glass tube for HCl. So it's a glass tube for HCl, and this is another tube for uh, uh, taking taking the gas into a flask that's containing lime water. So we have to ensure that this flask is immersed into the lime water. So let me see. So this is your lime water. This is your glass tube. This is your HCl. This is your conical flask. Okay. Uh, and this is your rubber seal. You can call it as cork with holes in it. So this is something what it looked like. So let's describe use a conical flask for the solution. HCl can be added to it via pipette, uh, sealed to the flask using a rubber stopper with tubing holes. Okay. A glass tube is used to collect gas and pass to another flask containing lime water. Make sure the tube is properly immersed in the lime water uh, flask. Okay. So the tube must be, or the lime water must be going, or the gas must be released in the jar, in the lime water uh, flask, when it is or inside the lime water, not above it, so that the gas properly interacts with the lime water and turns it milky. If you are just releasing the gas, it will just simply, you can say, not properly react with lime water. So this is how, I mean, you can write it. Again, I suppose I have tried my best. So, but you can, I hope that you have understood the process. And again, you can write it in a much better fashion than me. So going ahead, question 4, it says copper 2 carbonate reacts with dilute sulfuric acid at room temperature. The word equation for this reaction is shown. So copper carbonate, sulfuric acid, copper sulfate, carbon dioxide, and water. Okay, plan an experiment to determine the volume of carbon dioxide formed when known mass of copper carbonate completely reacts with sulfuric acid. Your plan must include the use of common lab apparatus, dilute sulfuric acid, and copper carbonate. No other chemicals should be used. Then your plan should be include apparatus needed, method to use, and measurements to take, procedures to ensure the volume is measured accurately. Okay, as accurate as possible. Okay, so again, you can always draw diagrams, and that is good too. So let's try to draw a little diagram to, let me draw it here. So say this is we have a conical flask, and we used a solid, this is copper carbonate. So you can measure it, measured weight. Okay. Then we have a cork over here, rubber cork, and then it's a gas tube that is connected to a glass syringe, or a syringe that is used to collect the gas. So, and uh, so you can also add a glass tube, add HCl to it, or something like this. Okay, or you can add a pipette to add HCl, volume of it, something like this. So this, so it starts it and make sure the HCl is in excess, and so let's see. So these are, this is your pipette, no, not pipette, it's actually burette. Write it as burette. Uh, you have a conical flask, you have this is your conical flask, this is your gas syringe. Okay, so let's try to write it. Using digital balance, measure and record weight of copper carbonate and place it in a conical flask. Use a rubber stopper with two tubing holes to seal the flask. Insert burette in the tubing hole and in one of the tubing hole and gas syringe to the other. Okay. Then your plate is ready. Then gradually, oh, gradually add sulfuric acid, uric acid to the glass. Last, make sure gradually add to the glass. What you'll see, effervescence of CO2 gas will be observed. Then keep pouring acid till the effervescence stops and no solid CO3 is seen in the flask. Okay. Shake the flask gently to ensure a complete utilization of CuCO3 and acid in excess. Okay. Then, so once you have done that, check the Meyer and record the reading on the gas syringe. Okay. Then you can say repeat the experiment, average out the reading for precision and repeatability. Repeat the experiment and average out the readings for precision and repeatability. Okay. So that's it. That's how you answer this question, and that's all for this exam. I think this is enough to give you all the 6 points for this question. And interestingly, in this paper, we do not have an example coming from the molds, which used to be a pet question for ATP papers. This time, they have changed the trend a little bit. So that is interesting. So it is a good possibility that from upcoming exam, they will be asking questions in similar pattern. But again, we cannot discard questions of concentration, moles, molarity, and etc., or the titration questions. But it's a little shift in pattern in the ATP paper. So Again, let's see how the next and upcoming exams go. And that's it from my side. I wish you all the best for your exam, and I hope that you have learned from this. If you have any questions, please write them in the comments. I will try to answer them as to the best of my ability. And if you want independent sessions, I'm also available. You can also reach out to me via the number provided in the details of this video, and as well as you can ask me for help via messaging me in the messages column below in this video. All the best and best of luck for your exams.